Let's finish up example 3. We did the calculus before lunch. We went to lunch, we refueled, and now we're ready to do the algebra. And it is the algebra that burns more calories. So I'm glad that we are now revitalized. Solving for dy dx is what we want to do next. Now, of course, this dx right here, you can call that 1. You wouldn't need to call it dx dx. But what we're going to do now is treat everything else as a constant. We're going to collect our dy dx terms. Now, here's what's interesting about something that requires implicit differentiation. And why did this one require implicit differentiation? I forgot. It had a y on both sides, and we could not solve it explicitly for y. There you go. In terms of x, yeah. That's why it was required. You're always going to be able to solve for dy dx after you take the derivative, because the derivative will always be a linear equation of dy dx in terms of the other variables. It will always be a linear equation of dy dx in terms of the other variables. So you'll always be able to solve for dy dx. And the way we do that algebraically is we get our terms, and again, we have 2 of them here on the same side. So I'm going to show multiple steps here. Dy dx is on the left minus secant y times tangent y times dy dx, or y prime if you're careful. And what does that leave on the right-hand side? It leaves, no, be careful. It leaves the 1, the dx dx, which is 1. All right, the next step from here is to do what? You have 2 terms. You're trying to get a single dy dx. You need to factor it out from both terms. Because they're not like terms, but we can still factor out the dy dx. Very important first step here. What do you get when you factor dy dx out of a dy dx? 1. Guess what the most common error is right there, students put? 0. Don't put 0. Minus secant y times tangent of y. If you get in the habit of just quickly mentally redistributing, you'll see that you got the right answer. And of course, that equals 1. Now, we're almost there. We have dy dx times something. All you have to do to solve for dy dx is undo the multiplication by dividing both sides by that big blob. So you get 1 over 1 minus secant y times tangent of y. And that is the derivative equation for the original equation. So whatever that graph looks like, if you wanted to know what the slope of the tangent line was at any given point, this would give it to you. And notice it is only a function of y, so it doesn't require any x. So this means that this graph up here probably doesn't pass the vertical line test, but it passes the horizontal line test. So whenever you use implicit differentiation, expect y's in your derivative, if not x's and y's. Lots of fresh green stickers out there. Okay, you got the idea? You got the process down, basically? Sure, okay. 1 is enough. Let's go ahead. Yes, I guess so. Let's go ahead to example 4. Find the slope of the graph of this at the point 1, negative 3. And I'm going to kind of break my instructions here because I tell you the order to do it. I'll just walk you through it. Find the slope of the graph of this function at that point. Well, you walk up to the problem and you're like, oh, why? Why are there so many y's? And can I solve it for y? I don't think so. Now, there is a cubic formula out there that we might be able to use, treating everything else that's not a y as a constant, but we have to know the cubic formula. You know what it is? Yeah, it's really long. And even if we did that, it might not give us a single equation as a function of y. It might be up to 3, and I wouldn't want to do that. So, you know, the good news is we don't need it, right? Who needs it? Because we're going to take the derivative how? Yeah, implicitly. The first step, d dx. Now, as you do this, again, you can shuffle terms if you want to. I just prefer to shuffle them afterwards. Nothing needs to be rewritten in order to be differentiated. Everything looks like it's ready to go. But before you go ahead and do that, put the d dx in front of both sides, which is indicating your method. Now, we all know by looking at your iPad/paper what it is you're doing. Here we go. We have 4 terms on the left. We treat each term individually. what is the derivative of y cubed with respect to x? It's 3y squared, or you could put parentheses around here, so you could say it's blob cubed, so it becomes 3 blob squared times the derivative of the blob with respect to x, which is what? dy dx. Yeah. So what we did right there is kind of indicative of what we're going to be doing. You're taking the derivative with respect to x. So everything that has a variable that's not x, you just take the derivative like you normally would, and then before you walk away to the next term, you multiply by d variable dx, in this case dy dx, the chain rule. So what would y squared become? 2y to the first times dy dx, right? 2y dy dx. Minus the derivative of 5y with respect to x is 5 times the chain rule dy dx. Now x squared minus x squared is going to be minus 2x dx. We don't need to write that, do we? Because it's just 1. And then, of course, this is where students kind of make a mistake because they're concentrating so hard on the left side. What's the rate of change of negative 4 with respect to any variable? 0. So it's 0, not negative 4. Okay, so again, if you want to take inventory, you can't solve for y, but you had 1, 2, 3 terms with y, and you had 3 y's in your equation. How many dy dx's did you end up with? 3. There you go. Now we got to solve for dy dx. So I've got 3 terms with dy dx. That negative 2x, he doesn't have a dy dx, so sorry, get to the other side. And we're going to factor out a dy dx from everything on the left. And we're left with 3y squared plus 2y minus 5 equals positive 2x. And all we got to do to solve for dy dx now is undo multiplication by dividing. So end up with 2x over 3y squared plus 2y minus 5. And that right there will give you the slope of the original graph at any point. Notice it has both x and y in it. So you need the ordered pair here in order to evaluate it. Yes? Well, good question. It was only going to be an explicit function of x if we could solve it for y as a function of x. Could we solve this equation explicitly as a function of x? No. So if you can't solve it explicitly, then when you take the derivative like we're doing, this is called implicit differentiation because we're taking a derivative of an implicit form. Does that make sense? Right. You're not going to be able to solve it like y equals, and then everything on the other side is just a function of x, not y. So you can't have y's on both sides. And if you do have y's on one side, it has to be y, right? So I guess you could have, like, on one side of the equation, you could have 2y minus y, right? Because that would equal y. It has to be y equals, and the other side, that would be for explicit. If it's not that, then it's implicit. All right, now let's answer the question. We were not interested necessarily in finding dy dx. We want the slope at 1, negative 3. So in Leibniz notation, now here's how you show that. dy dx evaluated at the point 1, negative 3. And this is similar to what the math print on your calculator uses. This is the Leibniz notation. It's called the evaluation bar or the when bar. The TI-89s actually have an evaluation when bar button. So you throw it like that, and then carefully, not carelessly or haphazardly, you plug in into your equation a 1 for every x and a negative 3 for every y. So here we go. We get 2 over 27 minus 6 minus 5. Free response, are you done? Could be, right? You don't have to simplify. But let's keep going because that's how we train. 27 minus 11, that's a 16. Of course, 2/16 is 1/8. Sweet. Now I know a little something about that graph, right? That graph, whatever it looks like at the point 1, negative 3, is increasing or decreasing? Increasing. Rapidly or not rapidly? Relatively not rapidly, right? 1/8 is a pretty shallow slope. It's going up 1 for every 8 it's going to the right. So most of its energy is translated horizontally, right? It's going to the right. If you want to think of velocities, it's going to the right 8 times faster than it's going up. That's kind of getting into vector calculus. Now, I kind of wonder what that graph looks like. Do you wonder what that looks like? I sure do. Alejandro does. Okay. Can you graph this in your TI 84/85/83 or /84 plus /silver edition? Possibly? What do you need to be able to do for your calculator that you have to graph this? You need to be able to what? You need to solve it explicitly for y. Yeah. Now you might be able to have some kind of clever circumvention of that. You might be able to solve this thing for x, right? And get a plus or minus and then graph it on your calculator and say, well, my actual graph is going to be rotated, okay? But there's a way to figure out what it looks like. But you have to go to the World Wide Web. And I'll show you what that is. The World Wide Web. I will show you what the World Wide Web is, in case you haven't heard of it. Let's get this real quick. All right. So anyway, here we are. This is what it looks like. If you go to Wolfram Alpha, it's an internet site, and it's just a massive number crunching internet website. It is great. It is great, right? Great. Depending what you're looking for. This is what the graph looks like, right? Does it pass the vertical line test? No. It kind of looks like the cross-section of like a basin or a ewer or a vase or something. But anyway, here it is. It graphed it. You can go to this website. We were looking at the point, what, 1, -3? Let's go to the point 1, -3. 1 would be right there. Go down to -3, which would be, I guess, right there. And if I were to draw the tangent line right there, you could see that it would be positive slope, but relatively flat, right? So there it is. So even though it's not a function of x, fails the vertical line test, we're still interested possibly in learning how fast that graph is changing there. How else could this equation be useful? Well, let's come back to the equation, and just looking at it, looking at this, I can determine right away the x value of the horizontal asymptote, right? Because what do we know about the slope of a horizontal line? It's 0. And if you set this entire fraction equal to 0, well, that's going to be when the numerator is 0, right? And what value of x makes the numerator 0? 0. Do you remember what the graph looked like? Did it have a horizontal tangent at 0? Yeah. Now, how would you figure out the y value there? You would actually have to plug in a 0 up here for x, and you would get y cubed plus y squared minus 5y equals -4, which could have up to 3 solutions, but in this case it only has 1. So that's not going to be very easy to solve. It doesn't look like it's a nice integer, but at least we know the x value. Now, what do you notice about the slopes right here and right here? They're vertical tangent lines, so the slope should be what? Infinity or negative infinity? Yeah? So what do we know about the derivative? Should it be defined there or not defined there? Not defined there. So if we go back to the equation, how could we use this equation of dy dx to find the x values or the y values where the derivative was undefined? It's a ratio, right? When is a ratio undefined? When the what is 0? Yeah, when it's non-zero over 0. So what we could do if we were interested in those vertical tangent lines is we could set the denominator equal to 0. Now, I don't know if 3y squared plus 2y minus 5 factors. It might not, but notice it is a quadratic, yes? And so it indicates that there could be up to how many values of y where the derivative is undefined? 2. And do we know, in fact, there are 2? Yeah, there are. So pretty nice that the equation will tell us something about the graph. So even though we can't like visualize that on our own calculators, there are things out there that are worth mentioning. And implicit differentiation kind of opens us up to a whole new category of equations that are functions of multiple variables and not just a single variable x, which, as you can imagine in the real world, there's a lot of things responsible for a lot of things, right? It's not just one variable. Yeah. Okay. I don't know what's responsible for the Astros blowing the lead in Game 4 and then losing in Game 5. But anyway, that's a different story. Find the slope of the graph of this now by doing it a different method. Now, example 5 is going to be like example 4, but I'm going to have you interpret it a little bit differently. If you were interested in not finding a nice cleaned up version of dy dx because either the instructions didn't say find dy dx or you didn't have to use it, if you just wanted to take the derivative and plug in a number to find the slope, You could certainly do it like we did up here. But notice all that rich, yummy algebra that we had to do right here. You might want to avoid that sometimes, right? You don't eat cake every day, every meal, right? It's a treat. Oh, you do? Okay. So here's what you could have done. I'm going to come back up here, and with the wonderful technology that we have available to us, I'm going to copy the derivative and paste it right here. That is the derivative, right? That's the calculus line. If you are interested only in the numerical value, there's no way to indicate it in Leibniz form, so what you could do then is just say at 1, -3, and what that does is it indicates your method. We all know what you're doing now. And now you're going to plug in first and then simplify rather than simplify and plug in. Why do that? We shall see. I plug in a -3 and I get 27 dy dx minus 6 dy dx minus 5 dy dx minus 2, which when I bring across becomes positive 2. Notice how quickly things start combining when you plug in first. You don't have x's and y's and non-like terms. You have numbers, which numbers combine very quickly. So 27 minus 11, that's 16 dy dx. You can even like throw a y prime in there. Is that okay? Yeah, I would say be consistent with your notation. I really prefer the Leibniz notation in this case just because, again, it preserves the slopey feel and you can see the independent, dependent variable. And most importantly, in this case, it does stand out quite prominently. But you get the same answer. And it's a lot quicker. It's a lot safer. There's less risk of making a careless mistake. So just kind of be aware of what the problem is asking. Are you just finding the numeric slope on your own? Did the question just ask for the numeric slope? Or did it ask you to find dy dx, the equation? And or are you expecting to use this for multiple purposes, like finding horizontal tangents and vertical tangents, et cetera, et cetera, et cetera, et cetera, et cetera. How many et ceteras are required for people to get the gist, et cetera, et cetera? Just one? One et cetera means so on and so forth and so on and so forth. So et cetera is not needed. But if you wanted to continue saying the et ceteras, could you then just say et cetera, et cetera? Et cetera, et cetera. So then the et ceteras get carried on ad infinitum.
But what if you want to use even more of those units of et cetera?
That's a gret question. This is calculus, and it would not be calculus if we did not go off on tangents quite often. Yes. Okay, let us try another example. But this time I'm going to let you do it. You do it. You do it. And I don't care how you do it. If it's just after the numeric slope. You want the derivative at 1 for that equation. I don't care if you take the derivative explicitly if you can, implicitly if you know how. Sure you know how. And then you simplify and then plug in, or plug in and then simplify. I don't care. You know what I'm going to be doing while you're doing that? I'm going to be talking, trying to distract you so you can't do it, just to develop your ability to focus and concentrate. Should I do that? No, I'm not. You know what I'm going to do as soon as I quit talking? Y'all are already well into the problem, I hope. I'm going to go back to the World Wide Web. You remember I showed that to you a little while ago? It's pretty nice. I think you'll like it. Be careful. It's very addicting. I'm going to go ahead and go back to that website, the Wolfram Alpha, and I'm going to type in this equation, and then I'm going to let it graph while y'all are doing this, and then we're going to meet back here in a little while. As soon as I quit talking, I'll do that. And then we'll kind of compare answers and see what we did graphically. How does that sound? Does that sound good? Anyone need me to repeat all that? No. All right. Okay, also, while it's up there, I'm going to go ahead and work the problem as well. Maybe we'll do a split screen here. Bless you. Bless you. It's a rather interesting problem. The derivative, hopefully, is the easiest aspect of all of this. How you doing? Your college essays on your phone? Yeah. Getting stuff done. All right. If you notice, it's not solved for y, right? And it's a y squared. It would be minus 2xy. I don't think it's worth trying to solve for y. You can use the quadratic formula, but that's going to still give you two equations, plus or minus, and we'd rather just work with one because we know how. So d dx to both sides. The derivative of y squared is 2y dy dx. The derivative of x is dx dx, or 1. The right side is a what rule? Product rule. So you can associate the 2 with the x and the y by itself. So the derivative of 2x is 2 times y goes for the ride, plus 2x goes for the ride times the derivative of y with respect to x, which is dy dx. Or you can call it 1 times dy dx, whatever you want. I decided to simplify first and then plug in just because I like to practice the algebra. If you never practice the algebra with symbols, when the time comes, you might not be able to do it. So everything's expanded out, so I can collect my two terms of dy dx on the left. That leaves the 2y over there, and the plus 1 comes over to join it with the minus 1. Careful inventory here. Okay, then I factor out the dy dx, divide through, and you end up with 2y minus 1 over 2y minus 2x. Almost worth factoring out a 2 from everything and dividing it out, but not 1 and the 1. I don't want to call it 1/2. So there's the derivative. And notice, in order to evaluate it, we need both a what and a what? X and a y. Okay, hopefully they gave it to us. I really hope they did, right? I really hope they did. Find the slope at x equals 1. And they didn't. Snap. Okay, no problem. Now, usually, you are given both the x and y, as we already saw. If there's no x coordinate and y coordinate given, there could be ambiguity, because there might be more than one point at that x value. But if they ever give you a single x value, it can indicate one of two things. Number one, it could be a hint to you to first solve for y. So if you ever see that, that's them hinting, you can solve it explicitly for y maybe, and you'll just have a function of x for your derivative. But we already thought about that, right? And we couldn't do that. So the other situation could be that maybe there is only one y value associated with it, and we can find it by plugging in. So that's what I did over here. At x equals 1, if you plug it into your original equation, you get y squared plus 1 equals 2 times 1 times x, or 2y. If you bring the 2y across, you have a really handsome quadratic trinomial there as a function of y, and it factors nicely. In fact, it's a perfect square trinomial. It factors into y minus 1 squared. And so there's only one y value associated with the x value there, and it's 1. So now we have our ordered pair 1, 1. And now we can bring it back over here into our cleaned up derivative, or you can bring it back up here to the top If you brought it up here, then on the next line you would have to say at 1, 1, and then plug it in and go to your numeric line, whatever. But when you plug it in, you end up with something interesting, right? You end up with 1 over 0. Now, what does 1 over 0 mean? Well, it means many things, right? First of all, it means DNE. The function value doesn't exist there. Why does it not exist? Because it's some type of infinity, plus infinity or minus infinity, which means that the graph of that function has a vertical asymptote. I guess I should say at x equals 1. And of course, all of those three things imply, since that's happening to the derivative, that the derivative has a vertical tangent line, or the graph has a vertical tangent line there. And I guess I have one too many there. There we go. Is this customary in the Spanish language to show extra excitement by putting inverted exclamation points in the front, like multiple? If you put them at the back, you need more in the front as well. Is it just as cheesy in Spanish as it is in English to put more than one? Posible, because, you know, you should really never try to fake enthusiasm by adding exclamation points.
We like vertical tangents, but not 3 exclamations like that.
That's right. I mean, how would you interpret something like that? Just food for thought. Or here's another one, right? That one's probably even better, right? Enthusiastically apathetic. I give it my ALL when it comes to doing nothing. Yeah, so we have a vertical tangent there at the point 1, 1. I wonder what it looks like. Well, we have it graphed right here next door, yeah? So if you go to the point 1, 1, here's 1, here's 1. Notice right there it appears that there is a vertical tangent line. And there is. We found it. It appears that there's another one over here. Its companion at x equals what? Maybe 0, 0. That's it. That's implicit differentiation. It's both fun and easy. It's fun and easy. Yeah, okay. Practice, practice, practice. Your test on Thursday, next Thursday, a week from today, will be through implicit for sure.